Hello, my name is THASARATHAN and I'm from group A2. Today I'm going to present about experiment number 4, which is rotary evaporatory system. So before that, let me define the meaning of evaporation. Evaporation is the process of removing vapor from a solution in order to produce a more concentrated solution. So in this rotary evaporatory system, we are using an application called rotary evaporator, which is also called roto valve. So this rotary evaporator, the function is it removes excess solvents from the samples by applying heat to a rotating vessel and reduce pressure. It also utilizes by lowering pressure than atmospheric pressure. In other words, there are many specifics added into this rotary evaporator system. One is it increases rotation. By increasing rotation, it also increases surface area at the same time and allows rapid evaporation due to higher surface area. Okay, now I'm going to discuss about the theory of this experiment. The basic equation for this single effect evaporator is Q is equals to UA and temperature difference. Q is the heat transfer and A is the area and T is the temperature indifference between the condensate and the concentrated liquid. This rotary evaporation is used widely in industry in order to separate low boiling solvents like N-hexane and ethyl acetate. Solvent of higher boiling points like water and any other chemicals is also permissible if the system allows a very low pressure. This rotary evaporative system works in two mechanisms, namely the centrifugal force as well as the frictional force between the wall of the rotary flask and liquid sample as well.
Hi guys, I'm DEVENDRAA here. I'm going to do on methodology part. So first of all, this is an overview of the rotary evaporator. Before we start the experiment, we have to calibrate the samples. So first of all, the samples of the sodium volume of sodium hydroxide is prepared and labeled. Then refractive index of this mixture is measured. So then later, refractive index, also known as RI, versus composition for the whole mixtures are plotted, as this will be the calibration curve for further experiments. So first of all, part A. Part A will do on the effect of different sodium hydroxide NaOH concentration during constant pressure and rotation. First of all, NaOH solution is prepared by adding 20 grams of NaOH into 100 ml of water, and this solution is weighed. Then next we have to set the parameter as follows. Water bar temperature 100 degrees, then vacuum pressure 119 millibar, rotation is 60 rpm. You have to run the process for 30 minutes and then measure the refractive index and weight of the liquid and vapor. Then repeat the experiment with 40 grams and 60 grams of sodium hydroxide in 100 ml of water. Part B is the effect of different pressure at constant NaOH concentration and rotation. So as the previous experiment, you have to do NaOH solution is prepared by adding 50 grams of NaOH into 100 ml of water, and the solution is weighed. Set the parameter as follows. Water bar temperature again 100 degrees Celsius. Now vacuum pressure will be 90 millibar. The rotation is 60 rpm. Run the process for 30 minutes and then measure the refractive index and weight of the liquid and vapor. Repeat the experiment with 150 millibar and 200 millibar of vacuum pressure. Then the last part is you have to measure the effect of different rotational constant NaOH concentration and pressure. So NaOH solution is prepared by adding 50 grams of NaOH into 100 ml of water, and the solution is weighed. Again, you have to set the parameter as follows. Water bar again 100 degrees, vacuum pressure 119 millibar, rotation is 30 rpm. Then run the process for 30 minutes and then measure the refractive index and weight of the liquid and vapor. Repeat the experiment for 60 rpm, 80 rpm for rotation setting. That's all.
Hi, I am KHAI. After the rotary evaporator experiment is conducted, raw data are collected for analysis. In this video, I will explain about the results section, which consists of calculation and graph. Now, I will explain the first part of the experiment, which is the effect of different NaOH concentration during constant pressure and rotation. First, we need to do the mass balance. Since we are at steady state, the rate of mass in is equal to the rate of mass out. Then, for an overall balance, F equals to L plus V. After calculated the value of F, we compare the value of F experiment by getting the percentage error. Secondly, we calculate the mole of water by using formula 1 gram per milliliter multiplied by the amount of water used in unit milliliter multiplied by 1 mole over 18 gram, and the mole of NaOH by using formula mass of NaOH used in unit gram multiplied by 1 mole over 40 gram. As we calculated the mole of water and NaOH, we can calculate the value of mole fraction of NaOH, which is taking mole of NaOH divided by the sum of mole of water and NaOH. Then we can calculate the component balance of NaOH by using formula FXF equals to Lx plus VYF. After getting the value of X experimental, we will compare with value of actual X by getting the percentage error. For the heat balance, since the total heat entering equals to total heat leaving, therefore heat in feed plus heat in steam is equals to heat in concentrated liquid plus heat in vapor plus heat in condensed steam. This assumes no heat loss by radiation or convection. Thus, FHF plus SHS is equals to LHL plus VHV plus SHS, which we can also written it as FHF plus S lambda equals to LHL plus VHV. As heat transfer in the evaporator Q is equals to S lambda, which is also same as UA delta T. The equation will become FHF plus UA delta T equals to LHL plus VHV. By making the equation in term of heat transfer area, the equation will finally be A equals to LHL plus VHV minus FHF over U delta T, where the value of HF, HL, HV and U can be found in the steam table, and we assume value of delta T is 10 degrees Celsius. Therefore, by substituting all the value into the equation, we can get the value of heat transfer area A. Finally, we will plot graph of concentration versus heat transfer area. All the above steps are the same for second part and third part of the experiment, which are effect of different pressure at constant NaOH concentration and rotation, and effect of different rotational constant NaOH concentration and pressure. That's all for the calculation of rotary evaporator experiment.
Assalamualaikum and good morning. My name is HAKIM bin ROSLI, and now I will present to you the discussion part about our experiment rotary evaporator. Let's proceed on. Okay, moving on, I will now discuss about the discussion part about our experiment rotary evaporator. For the discussion part, it is actually divided into 3 separate parts. The 3 separate parts resembles the 3 different variables affecting the evaporation rate. Part A will be talking about the different concentration of sodium hydroxide on the evaporation rate. Part B, the different pressure, and Part C on different rotation speed. Okay, for Part A, the different concentration of sodium hydroxide, we have the concentration of 10, 20 and 25 gram of sodium hydroxide per 100 ml. At higher concentration of sodium hydroxide, the rate of evaporation decreases due to increase in boiling point of the solution. Basically, as we increase the concentration of sodium hydroxide, the impurities in the solution increases. These impurities in turn increases the boiling point. As the boiling point increases, it will take longer time for the solution to reach its boiling point, thus it decreases the rate of evaporation. Next, the refractive index, the Ri, increases due to the increase of the density of the solution. As we increase the concentration of sodium hydroxide, when we measure the Ri, it will increase due to the increase of the density of the overall solution. For Part B, the measurement of different pressure, the pressure taken is at 120, 170 and 220 millibar. At higher pressure, we can see that there is a decrease in the refractive index because the high pressure makes the solutions more dense, and also there is also a decrease in evaporation rate because as the pressure increases, it will actually push down push down the water vapors onto the surface of the solution, making it difficult for the water molecules to change from liquid to vapor form. Thus, it actually decreases the evaporation rate. And finally, for part C, for different rotation speed, we measure speeds at 30, 60 and 90 rotation per minute. As we increase the rotational speed, the evaporation rate at this particular part, it increases, other than the two other parts which decreases, because when it rotates, at higher rotation, the centrifugal force is stronger. When the centrifugal force is stronger, it actually pushes the solution inside the flask towards the wall of the flask. This creates a constant film of the solution at the walls, which helps in the evaporation process. As the solution are being pushed to the walls of the flask, it becomes more direct contact with the heat. Thus, it helps in increasing the evaporation rate of the solution. Okay, thank you very much. This has been my part on the discussion. Again, my name is HAKIM bin ROSLI, and thank you very much for your attention.
Hi guys, my name is MAHER. I'm from group A2. I'm going to present our conclusion for our experiment. So in conclusion, we have found that this experiment has achieved all our objectives, which are the study of effects of the concentration difference in the evaporation rate, and the effects of rotation and the effects of different pressure. So at conclusion, we found that the rate of evaporation increases as the concentration decreases. And the second one, we have found that the rate of evaporation decreases when the pressure of solution increases. The third one, the last one, we found that the rate of evaporation increases when the rotation decreases. That's all. Thank you.